everybody. So far you have learnt viscoelastic characterization behavior in a strain control mode and a stress control mode test, and in a time sweep testing and in the frequency sweep testing mode. You have also introduced to material functions such as relaxation modulus, which was denoted as E, and creep compliance functions denoted as J, and you know that these functions are time control functions and it all depends on time factor. You also know in oscillatory mode we use a dynamic modulus function and a phase angle function to characterize the material behavior, and these functions are frequency dependent. So, these functions are valid only if you test the material in the linear regime. So, as of now we are clear about these functions. Now, the next is in the laboratory when you test the material, our time we have a time constraints. So, the testing is restricted, the testing time or a testing frequency is limited here. For example, if you see a relaxation test result for an asphalt, you see this plot, the time scale here is varying from 0, since it is in the logarithmic scale it is not starting with 0, and the maximum time scale is 1000 seconds. So, when you subject the material to a constant strain, something like this, let us keep this strain to be maybe an epsilon naught. The response of a material asphalt binder to this constant strain will be like this. Now, if you see this plot it is given as a torque. You can always convert the torque value to a stress using some constants, and this stress can be again converted to a relaxation modulus. So, if you see this relaxation modulus, it is a function of time. So, let us pick one temperature data. You have a various temperature data here. Let us pick one temperature data, maybe corresponding to 30 degrees Celsius. So, if you see this plot, the relaxation modulus trend will also be same as the torque trend. So, at 30 degrees Celsius, the modulus value depends on the time. So, as the time goes on, the modulus value is decreasing. Here in the while conducting the test, the test was stopped somewhere near 600 seconds. Now, what will be the response of a material beyond this? So, if you want to know the response of the material above after 600 seconds, so what to do? Likewise, if you see another factor here, we have different temperatures like measured at 15, 25, 15, 20, 25, 30, 35 and 40 degrees Celsius. You can see that the modulus function is also temperature dependent. So, we can write it as relaxation modulus to be a function of time and temperature. We will use a small t for time factor and capital T for temperature. So, we see that the relaxation modulus here depends on time and temperature. So, and one more thing is our laboratory testing is limited, we limit it to a particular time. So, we conduct only to a limited time scale, or in case if we conduct it in an oscillatory mode or a frequency mode, we limit it to a limited frequency. So, now if you want to extrapolate or if you want to know the response of the material beyond the test conditions, how to project it? So, that is what we are going to do it in this class. So, for doing this, we are going to use a time and temperature equivalency factor. So, we call it as a time temperature superposition principle. So, using this time temperature superposition principle, we are going to extend the limit of frequency or a time scale and construct a curve called as a master curve for a bituminous mixtures or a bituminous binder. So, the outline of presentation is going to be like first we will define what is time temperature superposition and then see the step by step process in constructing a master curve using a time temperature superposition principle. So, I will just read this time temperature superposition as such in the slide. So, time temperature superposition principle, in short we can also call it as TTSP. So, it states that effect of increasing or decreasing the loading time, or in case if you test it in an oscillatory mode, increasing or decreasing the frequency on the mechanical properties of a material is equivalent to that of either raising or lowering the temperature. So, in short you can write it as E. This E can be anything, E can be relaxation modulus, any material functions or any mechanical properties of a material. It can be a creep response or a creep compliance, or it can be even a dynamic modulus, or it can be even a phase lag or a phase angle. So, a modulus function or a phase angle function at temperature T and time is equal to the modulus function at some other temperature and time. So, we are going to use this equivalency factor in constructing a master curve. So, in otherwise you can see a example graph provided here. One is for a time control test, this is a stress relaxation experiment, and this is oscillatory shear testing or frequency sweep test. Now, if you see the stress relaxation experiment, so the stress is measured at different scale, different time scale, at different temperature. So, now this corresponds to a lower temperature 15 degrees Celsius and the this lower one corresponds to a higher temperature 40 degrees Celsius. As you go higher and higher with the temperature, the material relaxes faster. So, the lower one corresponds to higher temperature and the top one corresponds to lower temperature. So, now if you see, if you take an example of a stress value here, which is the stress value here is given in Pascal. So, now this is nearing 3.5 Pascal. So, nearing 3.5 Pascal, the stress relaxed from a maximum value to a 3.5 Pascal after, if you see the time scale for a 35 degrees Celsius, maybe after 90 seconds. The same stress here at this is at 30 degrees Celsius and at 35 degrees Celsius it happened at nearing 35 seconds. So, the stress value here, or in terms you can also equate it like equivalent modulus values, relaxation modulus. So, the relaxation modulus is constant at the time 35 seconds when you measure it at 40 degrees Celsius, or at 30 degrees Celsius if you measure it, it is at 90 seconds. So, now we are going to use this and shift all the temperature data into a single curve. Find the equivalency between a time and temperature and shift all the different curves here into a single curve, and that is what that single curve is what we call it as a master curve. Now, here is an example for a frequency sweep test. So, this is a frequency sweep test conducted at different temperature varying from 15 degrees Celsius to 75 degrees Celsius for a VG30 bitumen, and the variation in the dynamic modulus with the frequency for different temperature is shown in this plot. So, at higher temperature you can see the dynamic modulus value is lower, that is this is at 75 degrees Celsius. On the other extreme, lower temperature, this is 15 degrees Celsius curve. So, you can see a same dynamic modulus value at occurring at different frequencies when the temperature is varied. So, now we are going to equate this concept same dynamic modulus at different frequency and different temperature for constructing the master curve for a dynamic modulus. So, as the time temperature superposition says, modulus at specific time and temperature is equal to a modulus at some other reference time and reference temperature. So, now as I already pointed out, we are going to shift all the data to a single curve to get a master curve. Now, here the question is, we are going to match the modulus value for shifting. Now, how much you need to shift? So, based on the amount of factor which we are going to shift it, this TR is related to this T. So, the TR reference time can be given as T by AT. This AT is nothing but the shift factor. So, by applying a shift factors, the amount of shift at different temperature, once you shift it, all these data will merge into a single graph and nicely forms a single plot, something like this. So, now how to calculate this shift factor? So, we know that it is T reference is equal to T by TAT. This is what the time temperature superposition principle says. Now, what is AT? How to calculate this value? So, for calculation of this value, we just use an experimental data and equate the modulus value. So, now if you take a logarithmic of this equation, say equation A, you will get in log scale, you will get log AT to be equal to log T minus log reference temperature. So, now this same plot here which you have already seen, stress relaxation plot. So, in this plot, two temperature is highlighted here, one is 30 degree and other is 35 degree. The x axis time scale corresponding to 35 degree is taken as T ref and the x axis corresponding to 30 degree is taken as log T. So, now the shift factor here is log T, this log T minus log T ref, or otherwise this is going to be our shift factor. If it is in a logarithmic scale, we can write it as log AT. So, this is going to be our shift factor. We use capital T here, A capital T, because it depends on the temperature. So, you can see that if I want to shift this specific 25 degree curve to a reference of 30 degree, the shift factor value is different, the shifting value is different, and here from 30 to 35 degrees Celsius the shifting value is different. So, the value here, the shift factor, the amount of shift we are going to do it depends on the temperature. So, now if you see, we are shifting it from this is from a lower temperature to higher temperature. So, log T minus T ref. So, this is positive. So, if you shift for example 40 degree curve towards 35 degree curve, so now this becomes minus, because it becomes T ref minus T. So, this becomes minus AT. So, it is in the logarithmic scale. So, log AT will be in a minus number. So, number will be something less than 1 here. So, now the next question is what is the amount of shift. So, as we already seen that the shift factor AT depends on temperature. If you are going to shift from 25 degrees Celsius to 35 degrees Celsius, the value is going to be different. If you are going to shift from 40 degrees Celsius to the same temperature of 35 degrees Celsius, the value is going to be different. Both this, the shift factor is not going to remain the same. So, now, but how to calculate this? So, before even calculating the value of AT, are these two values related? Suppose if I name this as AT1 and AT2, are these two values related to each other? The answer is yes, these two values are related. For using a time temperature superposition principle, we can calculate the shift factor using a two approach. One is an Arrhenius equation and other is using a William Landel Ferry equations. This in short we call it as WLF equation. So, now let us see in detail how to calculate the shift factor using Arrhenius equation and WLF equations. So, this Arrhenius equation, this equation given here, equation A, it is a well known equation to all of us. Here tau given here is a time functions. So, it is a inverse of time function is related to activation energy U. So, by this in an exponential way. So, U here is an activation energy and K is Boltzmann constant. It is a constant value for a material. T is a temperature measured in Kelvin. So, we have a Arrhenius equation here and here one more function is here like nu naught. This is a frequency characteristics. Characteristics functions. Now, we have this function. So, this function says that inverse of time function you have it here related to an exponential function. So, if you take a logarithmic value for this equation, you will get log tau is related to inverse of temperature. So, 1 by T inverse of temperature. So, if you take a logarithmic scale, so this become a linear functions. So, you will get something to be a linear function like this, straight line like this. So, time function, logarithmic of time function is related to inverse of temperature. See, this is inverse of temperature. So, this is low temperature and this is high, this point will be high temperature. So, now we are going to use this Arrhenius equation to determine a shift factor. So, we know the shift factor is this. When you solve this both the equation, you will get log AT, which is nothing but to be a function of T and T ref. T ref is called as a reference temperature. And T can be any temperature. So, if I want to shift any temperature data to reference temperature, you can use this shift factor as per Arrhenius equations. So, this Arrhenius equation is based on an activation energy concept and it says that logarithmic of time scale, like logarithmic of time, it can be a relaxation time of a material varies in a linear pattern with respect to the inverse of temperature. See, we know that the relaxation time, if we assume this T to be a relaxation time, if we know that the relaxation time depends on temperature. So, at high temperature, let us quantify in a relative way high temperature and low temperature what happens. So, at very low temperature, the mobility of a particle ceases or more like a behave like a solid or something like a freezing conditions. So, at low temperature, this relaxation time will be high, relaxation time this will be high. At high temperature, relatively as you go lower and lower, this high temperature this will become lower, less. So, now this Arrhenius equations when this is validated for many polymers, it was found that at very low temperature it is not showing a real relaxation time is not showing a linear relation, but there is a deviation from the linear when it is nearing when it goes well away from the glass transition temperature Tg. Well away from a glass transition temperature, the Arrhenius equation deviated from a straight line and the value increased in a drastic pattern. So, now when to apply this Arrhenius equation is, since we assumed it to be a linear, you have to apply a Arrhenius equation only in this region, in this temperature region. So, generally now the next equation is William Landel Ferry equations. So, this William Landel Ferry equation was initially used for a polymers and it is based on the free volume concept. So, what is a free volume in a polymer? So, you can see a schematic of a picture here where you have a free space between a molecules and this free space is what we call it as a free volume. Volume of this free space is what we call it as a free volume. So, this William Landel Ferry equation assumes that free space in the material varies with temperature or free volume varies with temperature and it varies in a linear pattern, linear with respect to temperature. You can see this well established plot. So, you have a specific volume here and on other scale it is a temperature. You have two material, one is written as 1 and other is 2 here. One is a crystalline material and 2 is a amorphous material. You can amorphous material, bitumen behaves as an amorphous material, you can even assume it to be any amorphous material, let us consider as bitumen. See what is the difference is, you can see a decrease in decrease in a free volume as the temperature goes down. In a crystalline material the decrease happens all of a sudden, but in an amorphous material there is a rubbery behavior between a liquid and a glassy state. So, it is a gradual decrease in a free volume. So, William Landel Ferry equations assumes that this decrease in a free volume as the temperature goes down in the linear pattern. So, this WLF equations is based on the free volume. They have equated the viscosity relations, means they have related a viscosity with respect to the free volume and assume that the free volume varies linearly with the temperature, with function of temperature, and it varies in a linear pattern. With this assumption, this empirical equation was derived. So, the final empirical equations looks like this: log AT as a function of two constants C1 and C2. So, this C1 C2 constants universally we use C1 value to be minus 8.86 and C2 value to be nearing 100. So, exact value is 101.6. So, you can see that this A t is a function of C1, C2 and T is a temperature at which the data you wanted to shift, and Tr is a reference temperature to it's a temperature to be shifted. So, this log A t value depends on C1 and C2 value. So, you have a C1 and C2 value, a universal value to be like this. Now, can we use the same value for bitumen? The answer is many literature have proved it to be no. For predicting the response of a bitumen or applying a time temperature superposition for a bitumen, the C1 C2 value we cannot use this universal constant, but it will be C2 value will be somewhere nearing 100, and the C1 value will be somewhere nearing 10 to 20, but not exactly the same value. So, minus 10 to minus 20, not nearing the same value. So, we have different values for C1, C2 for a bitumen and a bituminous mixtures. So, now we have two equations, Arrhenius equations and WLF equations. We use these two equations to find a shift factor. So, once we find a shift factor, now next is to shift the value along an x axis. So, before doing that, we will see a relation between a Arrhenius equation and a WLF equations. So, Arrhenius equations you can see in a dotted line. So, this is Arrhenius equation, let me mark it as A, and the thick black one is WLF equation. So, we saw only these two equation, Arrhenius equation and WLF equation. So, let us not worry about what is this polynomial fit. So, now if you see the dotted line, the red color bigger dots here are the shift factor obtained from the experimental data. So, if you see Arrhenius equation here deviated from the data from the WLF equations when the temperature is less than minus 20 degrees Celsius. See, this is the shift factor obtained while constructing the master curve for a bitumen at a reference temperature of 26 degrees Celsius. So, this master curve was constructed for a dynamic modulus value. So, the dynamic modulus value was measured at different frequencies and at different temperature, and the master curve was constructed and the shift factor was estimated, and it is fitted to a WLF and Arrhenius equation. So, let us not worry how master curve was constructed as of now, we will just look into the deviation from Arrhenius equation and a WLF equations. So, there is a common temperature range here where both Arrhenius equations and WLF equation is applicable. So, generally as the temperature goes higher and higher or high temperature range, we prefer Arrhenius equation, and at low temperature range we prefer WLF equations. But you can see a common temperature range where both the Arrhenius and WLF equations are applicable.